All right, let's jump right into this explainer. Today, we're unpacking a massive, compounding environmental crisis. We're looking at the severe threats devastating the Vietnamese Mekong Delta, and we're pulling our insights directly from a pivotal study published by researchers at Kyoto University and Three Low University. These scientists actually went out into the field to track exactly what is happening to one of the most important river systems on Earth. It's an intense story of human engineering, climate change, and an ecosystem that's being pushed right to the absolute brink.
To really wrap our heads around the sheer gravity of this situation, we have to start by looking back at the drought of 2015 to 2016. Because, this wasn't just your standard dry season. It was the absolute worst drought this region had experienced in 90 years. Water levels plummeted to their lowest point since 1926. It was a massive wake-up call that something fundamental in the hydrology of the region had just broken down. Exacerbated by El Niño, sure, but deeply intertwined with human actions upstream. And that forces us to ask a pretty terrifying question, doesn't it? What actually happens to a thriving, massive human ecosystem when a mighty river is starved of its natural flow? The Mekong River isn't just water. It is literally the lifeblood of multiple nations. It delivers sediment, nutrients, and the seasonal flood pulses that have dictated life and agriculture for centuries. When that natural rhythm stops, the consequences are immediate and they are catastrophic.
Just think about the sheer spatial scale of the Mekong River Basin. We're tracing it all the way from the high elevations in China, where you have clusters of upstream energy developments and dams, flowing down through Myanmar, Laos, Thailand, Cambodia, and finally spilling out into the ocean. The river is essentially a connected highway, which means whatever happens way up there at the top sends a very direct physical shockwave all the way down to the bottom. And way down at the end of that line is where we find our specific focus today, the incredibly low-lying Vietnamese Mekong Delta. It's this dense, intricate network of rivers and channels branching out toward the sea. Historically, this beautiful, fertile region is celebrated as Vietnam's agricultural rice bowl. But it's also a highly delicate, perfectly balanced environment. It relies entirely on the freshwater and sediment washing down from upstream just to keep the ocean at bay. The crucial takeaway here is that we aren't just talking about abstract ecology, we are talking about real human lives and staggering economic stakes. 17 million citizens call this delta home, and their livelihoods depend heavily on agriculture and aquaculture. Plus, it is incredibly flat and vulnerable, averaging just 0.7 to 1.2 meters above sea level. Rice makes up a massive 90% of the planted crops here. So, during that 2015 to 2016 drought, the water shortage and resulting salt infiltration utterly ruined about 159,000 hectares of paddy fields. Hundreds of thousands of households literally didn't have fresh water for basic daily consumption.
Section 1. The upstream culprits, damming the mighty Mekong.
Now, while climate events like El Niño definitely play a role, the dozens of megadams currently existing, under construction, or planned along the mainstream Mekong are fundamentally and permanently rewiring the river's natural hydrology. These megadams don't just hold back water, they alter the very behavior of the river. By storing water to generate electricity, they release drastically less water downstream, right when the delta needs it most, during the crucial flood season. They also trap the vital nutrient-rich fine sediment that the delta desperately needs to replenish its soil and keep its elevation up. On top of that, shifting the natural flood timing means the downstream freshwater pressure just drops, which allows the ocean's saltwater to creep much earlier and much deeper inland. Researchers proved this by looking at two distinct timelines. They starkly contrasted the relatively undisturbed pre-dam period, which was between 1980 and 1992, with the modern post-dam era from 2008 to 2015. And the data reveals an unnatural and honestly dangerous reduction. During the flood season, water levels in the later period dropped by a full meter compared to earlier decades. The duration of the seasonal flood has also been severely shortened. Basically, the natural beating pulse of the river has been flatlined by human engineering. Section 2. Tracking the invisible threat, the forensic science of salinity. To actually understand the scope of this creeping disaster, scientists had to get out there, literally waist-deep in the gritty reality of the river. Using specialized infinity turbidity and salinity meters, they gathered high-frequency data, taking readings every 15 to 30 minutes. They needed to understand exactly how sediment was moving and exactly how fast the salt water was invading the delta during tidal shifts. It is heavy, difficult field science, but it's absolutely vital for tracking the damage. By strategically spreading these instruments all across the upper and lower parts of the delta, places like Tan Chau up north and Din An down near the sea, they built a comprehensive monitoring network. And what they found? Well, it was alarming.
During the 2015 to 2016 drought, they tracked saltwater choking the Haw River up to 55 to 60 kilometers inland. That is 20 to 25 kilometers further than normal. It's a massive, completely unprecedented penetration of the ocean right into the freshwater system.
You see, salinity intrusion is basically a silent killer for this ecosystem. It's when ocean saltwater infiltrates freshwater rivers and aquifers. And the thing is, rice productivity plummets dramatically with even a tiny increase in salt. The study points out that for every single gram per liter increase in salinity, rice yields decrease by half a ton per hectare. So this deeper intrusion isn't just a minor inconvenience, it's a literal death sentence for local crops and the millions of farmers who rely on them.
Section 3. A salty, sinking future, projecting the Delta's grim forecast.
Unfortunately, taking all this forensic data from the past and present only leads us to an even more alarming forecast for the future of the region. The researchers didn't just look backward, they modeled what happens next. And folks, we are looking at a compounding disaster. It's a brutal 1-2 punch. On one side, you have the proposed construction of 11 new mainstream dams in the lower basin across Thailand, Laos, and Cambodia. On the other side, climate change models are projecting a 47-centimeter sea level rise for the delta. When you combine a sinking, sediment-starved river with a rising ocean, the math gets very scary very quickly.
The resulting shockwave from these compounding threats is, frankly, massive. Hydrodynamic models predict that those 11 proposed dams will cause a maximum discharge reduction of about 15% across the delta. But when you factor in that 47-centimeter sea level rise, you get a devastating 220% maximum water level increase at places like Mai Tho. We are talking about severe, intense coastal flooding that will just drown the edges of the delta.
As the study explicitly warns, and I'll just quote this directly because it's so important, such phenomena are more likely to result in an increase in salinity intrusion, coastal flooding, and lack of fine sediment and natural nutrients to the VMD's floodplains. This practically guarantees a future where the delta is squeezed from both ends. It'll be choked by salt and floods from the sea and completely starved of the water and natural sediment it desperately needs from the river to survive.
So, as we wrap up this explainer, I want to leave you with a pretty massive, pressing question. How can nations balance transboundary water sharing and energy development before fragile, life-sustaining ecosystems like the Vietnamese Mekong Delta are just lost forever? The data shows us exactly what is happening. The real challenge now is whether policy and international cooperation can catch up before the rice bowl runs completely dry. Think about that one for a bit, and we'll see you in the next explainer.
A river delta survives on a precise balance of water and sediment. When the boundary conditions fail, the result is total physical breakdown. In 2015, the Vietnamese Mekong Delta entered a period of hydrological failure. Water levels across the region dropped to their lowest recorded point since measurements began in 1926. The delta is a low-lying system, averaging 0.7 to 1.2 meters above sea level. When the river's outward pressure dropped in 2015, the ocean rushed into the void. Saltwater intruded 60 kilometers inland, devastating 159,000 hectares of agriculture. This saline wedge pushed 25 kilometers beyond historical averages, aggressively moving up the Tien and Hao rivers. This hydrograph tracks flood season water levels at the Tan Chau station. The 2015 curve reveals a massive hydraulic deficit, plunging exactly 3 meters below the baseline established in the year 2000. While El Niño naturally reduced basin rainfall that year, a 3-meter deficit suggests a massive anthropogenic variable is overriding the natural climate cycle. To diagnose that variable, we have to look past the delta to the 475 cubic kilometer Mekong River basin. The upper Mekong in China sits 4,000 kilometers away from the disaster zone, yet 80 to 85% of the delta's flow entering through the Tien and Hao rivers is generated entirely in these upstream regions. The system runs on a strict seasonal rhythm. 90% of the region's rainfall occurs between June and November. The dry season is highly precarious. Between January and May, the delta is entirely dependent on upstream baseflow to maintain its internal hydrodynamics and agricultural viability. Because the downstream symptoms are separated from their upstream drivers by thousands of kilometers, analyzing the collapse requires isolating independent variables. Understanding the delta's failure requires tracking how upstream transboundary infrastructure synergized with sea level rise to rewrite the mechanics of the region. The primary anthropogenic variable sits in the upper Mekong, the Lanchang hydrocascade, which began construction in China in the late 1980s. The massive Nuajadu and Shawan dams came online and began exerting maximum influence on the river's hydrology after 2008. This volume chart illustrates the mechanical disruption. Optimizing for electricity generation requires operators to aggressively fill their reservoirs exactly at the onset of the wet season, severing the natural flow release. This retention cycle strips the downstream delta of the water volume and flood timing it relies on to survive the dry months. This hydrograph tracks telemetry data across 5 assessment periods. Between 2012 and 2015, base flood levels in the delta averaged a full meter lower than the pre-Cascade era of the 1990s. The missing water dictates a critical temporal shift. The onset of salinity intrusion in the delta now occurs 1 full month earlier than it did before the dams were built. Maximizing transboundary water for localized electricity generation breaks the natural timing of downstream hydro regimes. Upstream water retention triggers a secondary physical impact, the morphological starvation of the delta itself. Reservoirs capture both the river's water and the fine silt and clay necessary for deltaic accretion and floodplain fertilization. Upstream telemetry data is heavily restricted.
To map the deficit, researchers deployed high-frequency turbidity and salinity sensors directly into the delta. The central VOM-NOW station connects the Tian and Hao rivers, with sediment data acting as a proxy for the delta's structural health. This plot of suspended sediment concentration at VOM-NOW reveals a decaying system. By 2015, sediment loads had plunged to just 1/4 of their 2011 levels. Without a constant influx of fine sediment, the delta loses the physical mass necessary to rebuild its shorelines and defend against coastal erosion. Estuaries rely on a primary natural defense mechanism, hydraulic counterpressure. Historically, massive discharge volumes from the Tian and Hao rivers provided the physical hydraulic pressure required to push back the encroaching east and west seas. This structural flowchart isolates the intersection where anthropogenic flow reduction meets climate change, triggering systemic failure. Upstream dams dictate the river's discharge on the left, while the climate dictates the sea level rise in the center. The current climate-driven sea level rise of 3 millimeters per year now pushes inland against severely weakened riverine resistance. A dense, heavy wedge of saline ocean water aggressively creeps along the riverbed, overpowering the starved, retreating freshwater current above it. This loss of hydraulic counterpressure allowed the saline wedge to push 60 kilometers inland during the 2015-2016 drought. The Vietnamese Mekong Delta functions as a regulated anthropogenic system running on a severe deficit. Now, a compounded threat is entering the system. 11 newly planned and under construction mainstream dams, located in the lower Mekong Basin across Laos, Thailand, and Cambodia. These new structures will choke the system's baseline equilibrium further, trapping even more water and sediment before it can reach Vietnam. This projection model maps a dual threat. Bringing these 11 dams online will result in a maximum 15% reduction in vital dry season discharge reaching stations like Ken Ta. Stacking regional infrastructure without an integrated flow budget mathematically guarantees water deficits downstream. Modeling the combined impact of 11 new dams and 47-centimeter sea level rise reveals the projected limits of the delta's resilience. The results are paradoxical. While upstream base flow drops, localized water levels in the delta at stations like Mita are projected to increase by 220%. This massive localized increase is driven by backwater effects. As the river channels are starved of discharge, rising tides and storm surges easily overpower them, causing severe coastal inundation. The ocean surge pushes backward up the low-pressure river channels, forcing saline water to rapidly overtop the banks and flood the interior. During the 2016 crisis, the system was so fragile that Vietnam had to request emergency water discharges from China just to survive the dry season. This system is home to 17 million citizens whose agricultural livelihoods depend entirely on a predictable hydro regime. Unless transboundary water management accounts for the coupled impacts of upstream retention and sea level rise, the Mekong Delta faces a permanent agricultural and morphological retreat.